So we'll briefly go through assessment 2 before we start on skill structures tonight. So very similar format and approach to assignment 1. For this task, you're required to provide a report comparing and evaluating structural cladding and service options for a multi-residential dwelling. So same, except we've added multi-residential dwelling. So the proposed building design is on the learn site. So you'll see plans for it there, same as in the residential section. You must include a reference list of all websites, manufacturers' guides, and other sources of information at the end of the project. So please keep track of where you've sourced the information from. Fantastic. Structure, research and evaluate structural systems for the roof, walls, suspended floor for level 1. So same as the previous assignment, but we're talking about a 2-story multi-residential building now. So we've got suspended floor level 1. Several different options we could go with there. We could go with timber trusses. We could go with timber I-beams. We could go with steel platform flooring or suspended steel flooring. We could go with a suspended concrete slab. We could go with heave power floors, depending on their spans. Like the largest one span about 6 metres. Can't think off the top of my head whether we can fit that in to that building. I think we can. So heave flooring is also an option for that building. So plenty of options for a suspended floor. When we think about suspended floor, we want to think about compatibility with fire and spread of fire. So the containment between floors. So of course, timber is possible, but there are issues with that. And so these have been updated. So these headings are different from in the first assignment, or some of them are different, some of them are the same, but very similar sort of structure. So think about why the construction system is suitable. So you'd say timber is suitable because it's really cheap. You could say suspended concrete slab is suitable because it's strong, get large clear spans, it contains fire well, it is very quick to build, it is very quiet, there's no significant noise transmission between floors, etc., which is what you want in a multi-residential building. So we can think about why that construction system is suitable. Material properties. You can talk about the properties of various materials chosen. Fire resistance properties. Any coatings required? So with some flooring systems, there might be issues in regards to what coatings you can put on there.
Oh, sorry, suspended floors, do they have fire resistance properties?
They do, yeah. So there are engine. So certainly with a so this is where you're going to have to refer to the National Construction Code, and you're going to have to find out certainly what class of building it is, what type of construction it is, and what fire resistance levels you're going to need. So that's asked for here. So once you do that, that will play a little bit into what you say up here.
Okay.
So, but there are engineered systems for timber framing that contain fire within spaces. So you can research those. Compatibility, interaction with other elements, nothing new there. Health and safety issues, durability. But then this is the new one, compliance requirements, or it's broken. Compliance requirements is the other one, but this is broken down into these sections. What class of building is it? So have a look at the National Construction Code. For the class of building, you should be able to determine that fairly quickly and easily. From there, what type of building is it as defined in the BCA Part C1? So we look in the index of the NCC, go to Part C1. the type of building. We'll need to define what class of building it is first. So follow this through step by step. So step 1, class of building. Step 2, type of building defined by C1. And then the next step is what are the minimum construction requirements, FRL, BCA specification C1, 0.1 to 1.4. So it'll, when you find your type of building, in that section you'll find a reference to this area for the minimum construction requirements, FRL. This is a bit tricky. This bit, navigating the National Construction Code is certainly, yeah, it does my head in, but I've done it a lot. So, yeah, it'll do everybody's head in. It references itself. Yeah, it jumps all over the place. It references itself back and forth. But that's the nature of that document and large documents. So I expect that you may have some issues with that. We won't run through that tonight. I think it's best I give you guys the opportunity to try to navigate it yourself, because that's the way you're going to learn. But if people are having issues with that, we can have a look at that in week 9. And then, following on from that, research and evaluate 2 different wall cladding systems, different from task 1. So this one we can, it's giving you some options there: aerated concrete, brick, concrete masonry, other confirmed with lecturer. You can pretty much just choose other if you think. I'm fine with you choosing whatever you want as long as you can answer these questions on that. So, also research and evaluate 2 different roof cladding systems. For each wall and roof cladding system, consider the following: advantages and disadvantages for each cladding option, limitations, size or application, environmental impact, thermal properties, compliance requirements. So that's all fairly straightforward. The next thing is compare the advantages and disadvantages of different air conditioning services. Make a recommendation to your client based on your research and indicate the location of the service on level 1 floor plan. So this is where it works best if you grab a PDF. I'm pretty sure the plans are in there as PDFs. So import that PDF into your report and then just draw on that with your program to indicate where the air conditioning service should be. So do some research into air conditioning services. Think about the space. Think about how it will be used. Now, air conditioning, I'm fine if you just do it as cooling, but if you do heating and cooling, that's also fine. Because typically, air conditioning for these sort of spaces are the systems heating. And then just the note that was on the first one. So where pertinent, include structural details of the building system chosen. These details may be sourced from manufacturer's product literature, etc. The details may be self-generated either via a CAD program or hand-drawn. So if there are any details you think are good to put in there, by all means, put them in. And that's it. Does that make sense to everyone? Yes, so it's much the same as number 1, except you ask for a little bit more work in regards to compliance. That's it, and some research into air conditioning systems and to make a recommendation. Yeah, let's have a look. Certainly hope I've got a plan up there still. Just go back. Assessment 2 drawings. So, ground floor, first floor. Elevations. Incredibly up section. Here we go. So, once again, incredibly simple building. And
so we need to talk about fire rate between the walls as well?
yes. Yeah. So when you find out what type of construction it is, and you determine FRLs, they will give you FRLs for floor, wall, and roof. And so you need to talk about each of those. But they're all there right next to each other. So you'll say floor, 60, 60, 60, wall, 90-90, etc. No, you don't. Because of the class of construction that it is, we've got less than 12 occupants in the building. There are no specific requirements in regards to multiple fire exits and signage, etc. But they've got dimensions on there as well, which may play into what you choose to do for floor as well. We've got 13 metre or potentially 13 metre span from that lower section if we're not supporting that mid-span by any columns and beams. That's the lower. So a large open area for the car park. Yeah. You can say, let's make this cheaper. Let's chuck some columns in here, break up our spans, and have a far cheaper floor system. You're talking about options. You're not making recommendations, but you're putting out options there. So that's something you may want to speak about. Between them, I think 16.83. It is. So. Yeah, no, the spans can be continuous between, so the point. I don't know. What is? Yeah. Okay, you might be right. Yeah. Yeah.
So that's how
Yeah. Because it's a mid. Yeah, I don't know. I know there's definitely a ratio for cantilevers, but mid span I don't think there is. But
it's something
you can. Yeah. So tonight's lecture is on the use of steel, and this is, I guess, this is one of the aspects where your technological development in public architecture and commercial and industrial construction starts seeping into residential and enabling some of the more fantastic things in residential architecture. Steel is a big driver, or the technologies around steel is a big driver of that innovation. Steel sections come in different shapes and sizes. They are hot rolled, so heavy gauge, want to be 10 millimeters thick, or you got hot rolled sections thinner though, or cold rolled, light gauge, 1 to 3 millimeters. So that's the really thin stuff. So looking around this room, those cable trays, cold rolled, of course. These, they're pretty hard to see now. There's those large columns out there, and most definitely hot rolled. Yeah, all your members in those roof trusses there are hot rolled. We've got a large hot rolled C channel here as the bottom chord of this truss. So sections are often referred to by abbreviations. It's important to memorise a shortened name. The following slides feature commonly used steel sections. One member you're most likely to be familiar with is an I-beam, typically referred to as a universal beam, or UB. A UB differs from a UC only very slightly. Actually, can anybody tell me what the difference between a universal beam and a universal column is?
column should be a column.
Yeah. That you may think that is that's funny because the obvious answer, but the shape of that hot rolled section is dictated by its function. You get people using universal columns as beams, and you get people using universal beams as columns in scenarios. But to draw a cross section through a UV and a UC, I'll exaggerate it slightly. So that's, I'll take a little bit off the sides, exaggerate it even more. So that's our UV. And that's our UC. If I was to draw a line around the outside of this, I'd get a rectangle. This one, I'd get a square. The reason we have a square-based section for a column is because we've got forces coming at columns from this direction, from this direction, from this direction, etc. The forces come from all sorts of ways when you've got a column. When you've got a beam, most of your forces are coming down like this. And to resist those forces coming down, we deepen the section. Because the further we put this flange away from that flange, the stronger or the more tension that flange will take.
Yeah.
So, however, we can't, if we wanted to, so universal beams and universal columns have standard sizes and depths and flange widths and web thicknesses, etc. Within the slides, there's not a table for it, but I might have a quick Google search for a table that shows you all those sizes, web thicknesses, etc. So you're not going to go to one steel and say, oh look, I want you to make me a 500 UB with a 5mm flange web thickness. They're not going to do it. They'll say, nah, we do 500 UB with 8mm minimum, etc. So 500 UB, 51, which is like 51 kilograms per linear meter. But you could, let's say you can go talk to the steel supplier and say, look, I want one with a really big web and small flanges. That essentially, in this direction, makes that universal beam much stronger for its weight. But the reason we don't go producing steel sections like that is, yeah, exactly. There's always going to be some torsional stresses placed on this, and we apply a large load there, it's going to go like that, or something. So they do come in standard sizes for that, for that reason. But as you look around, as you walk around, you will see columns used as beams and beams used as columns. In fact, I think what we should do after this lecture is actually take a bit of a walk around the TAFE building and look at the use of some of these hot rolled sections in their applications, because there's being an old factory, there are some interesting uses of these sections. So that's universal beams and universal columns. Can anybody think of what a TFB might be? Yeah. Yeah. No, that's it's tough. That's what's called a tapered flange beam. So So our universal beams like this, we have a flange which is the same width all the way through, bar this little section here where there's a slight radius that ends into the web. But our tapered flange beam is like this. Well, that's exaggerated. In reality, it's a far slighter angle. It's slighter than that. It's more like that type scenario. But that tapered flange beam, that's handy in some situations because it concentrates steel here around the web joint. So we end up strengthening our web a lot more for our cross-sectional area of steel. So we're taking steel away from where it's not really needed, right at the outside of the flanges, and putting it here at that web junction where we want more sideways rigidity without having really wide flanges. Not only are things like universal beams, universal columns, C-channels, etc. used in steel framing like this, they're also used for retaining walls. A lot of people seen concrete sleeper retaining walls. So in that scenario, a typical rule of thumb is if you're going a metre out of the ground, you go a metre into the ground as well. With your universal, say your universal beam. The reason I thought about that is you should make sure that you do not use tapered flange beams or buy tapered flange beams for that use, because either your concrete sleepers fit nicely into your universal beams with a bit of packing at the back here like that. But if you do a tapered flange beam, you'll find you get into issues, and you're packing behind there, and it'll want to force it apart. So the depth of the profile generally precedes the abbreviation on drawings. So if you do work as a drafter for a structural engineering firm, you will be writing that a lot. 310 UB, or 200 UB or 150 UC, or a lot of that. Those abbreviations are used very commonly to denote structural steel members.
You also understand when you're reading the plans of them, even if you don't.
Yes, yeah, or even if you're not drawing them, yeah, if you're reading them as well. If you see bits, C1 UC310, now you know what that means. Column 1 is a universal column 310. That 310 relates to this distance between the top of the flange, or top of this flange, and the bottom of that flange. So it's about their width. There are also, we could get, for example, a 310 UB42 or a 310 UB51. That 42 and 51 are also important things to understand. That relates to how much it weighs per lineal metre. The reason we want to know that is because that is a very quick way of telling us what the web and flange thickness is. So you're not going to write universal beam 310, 8mm flange thickness, 7mm web thickness. You're going to say UB 42. And so that tells us how much steel there is in that piece. And so if you are specifying a beam or referring to someone's plans as specified, that is an important number, because if it specifies a UB 310 52 and you buy a UB 310 48, that UB 31048 may not take the load that it's designed to take. All of these, so within so we've got a link here to the LiceArts guide, but there are many different steel producers and suppliers that produce these universal hot roll sections, and they will provide dimensions on there of the sizes. They're all the same because they're universal. But what I suggest you do, this is a good thing if you're going to be designing yourself or working in an office, is grab CAD drawings of these universal beams and have them as blocks. Yeah, so just have them ready as blocks. So if you ever need to if you ever need to know exactly what width, because it's never exactly 310 millimeters, by the way, it's always 310 or whatever. If you need to know these sizes directly straight away, you just grab that block, put it in CAD, and measure those bits you need, or you just grab it and stick it in, see if it fits where you need it to fit. So having those drawings as blocks is incredibly handy. So got beams and columns. We've also got what's typically called a C channel, and we can understand why it's called C channel, but it's also called a PFC. So that's because, well, it's PFC for parallel flange channel. We want to denote that as a parallel flange channel because we don't want to get it confused with a tapered flange channel. So it's shaped like the letter C, often referred to as C channel, utilised when a flat side is required against walls or the edges of canopies, etc. So it can be used for pitching. It can be used in this example as the bottom chord for that truss, because that, C in an upside down fashion like that helps locate members easily. But where we don't need the strength of a universal beam, we can use a C channel, save on steel, so save on cost, but also save on weight. But yeah, I think I drew a detail last week of where we've got part slab, part timber floor construction. You use a parallel flange beam in that scenario to pitch off of your concrete slab. UA stands for unequal angle. That's where we have one of the flanges longer than the other. Or its more common cousin, the equal angle. So EA is also a thing that you'll see on drawings quite a lot. Equal angles are fantastic also for pitching from. So for securing to a point and using that for pitching. Good for edgings on things. Really good for bracing, for making very strong bracing in large sheds, for example. There's quite a few equal angles used around here. We've got equal angles for webs within the trusses. We also have what are we called? Mullions. It's a vertical support through the web in that truss. The purpose of that, I think, there would have been some purpose for that when it was previously a factory in here. Don't have that purpose. Also for the roof purlins, we've got equal angles right up the top there, the roof purlins as well. You see that just on the underside of the insulation there. See that going between truss to truss?
Oh, the smaller ones?
Yes, yeah. So the ones heading in this direction, right up the top, they're also equal angles. SHS denotes a square hollow section. Typically used as columns. Their cross section can be much smaller than their concrete or timber equivalent. So one of the reasons we use steel in, or particularly in residential construction, is because we want to be supporting, supporting loads through large spans, but we don't want a lot of depth in there. So, for example, we have a large window opening, but then that window opening is right below a floor or a roof. We don't have much space in there to use a piece of timber. We can use a piece of steel. And the square hollow section is perfect for that, because all the steel is located on the outside where the forces are the greatest. Our forces of compression and tension are the greatest on the outside. In the centre there, where the forces are more neutral, it's hollow. So it's efficient use of materials, so it's efficient use of weight and money. But we've got flat sides to fix against as well. And if it's a fairly thin SHS, we can also tech screw through it. So we can fix to it quite easily. You also have welded fixings.
Yes, welded tube.
Yes, yeah. I haven't seen it produced, but there is a line through it. Yeah. Right. Yeah, they do it very well. So you don't see them failing the welders. Yeah. So it's very thorough weld. Can anybody think of what a CHS can stand for? Cylinder hollow section? 10 points. Yeah. Well, circular hollow section, but yeah, cylindrical hollow section. Yeah, fantastic. And RHS. So RHS is something that gets referred to quite a lot. That's a rectangular hollow section. Rectangular hollow sections are fantastic simply because they place essentially this flange further away from that flange. So where we have our SHS, which is great for use as a column where we've got forces coming from all directions. RHS is fantastic as a column where we've got forces coming from one direction, or as a lintel or a horizontal member in a portal frame, something that works horizontally, but also used in fencing and things like that, wherever we have a predicted load coming from one direction or in one plane direction. Cleats, yeah. So typically we join our steel sections, or our hot rolled steel sections, with cleats. So they are small members which are welded on to those. In this case, we've got an RHS under here and a cleat welded on to that RHS. Oh, yeah, definitely. So steel fabricators have to be very exacting typically with their fabrication. If you've watched Brand Designs enough, you would have seen an episode where they're freaking out about, is it within that 10 millimeters or so of play that we have to get in this big steel frame in place, etc. So they have to be manufactured to exacting standards, because once bolted together, once set in place, there's generally not a lot of room for movement and free play. So essentially a flat piece of steel, cleats are often used to join two steel sections together, often welded to one component and then bolted to the other. There are also, so here we've got our bolted fixings. at times we can have slotted holes. So we have, if we want to have more free play within the point of construction, we can have a cleat like this with a circular hole, and that's a bit exaggerated, or an elongated, well actually we'll elongate that hole in this direction, sorry, to enable some rotation of our fixing. However, more typically, this is the way it's done for exact fixing on site. So we could use, let's say we're going to make up a square portal frame for the end of a square townhouse or something. Or let's not call it a townhouse. Let's have a detached dwelling that's got a lot of wind coming from this direction and a big window here, or two big windows here. You know, we can't put any bracing in there anywhere. Our client, you know, standing out there looking at the ocean, doesn't want to have big steel bracing going like this behind the windows. We can't do that. So we'll manufacture a steel portal frame to go in there. We've got our SHSs here, SHSs or RHSs, depending on what the expected forces are. So if it's a very long skinny building, and we've got a lot of wind coming from this direction, we're going to use RHSs in this portion here, because the majority of our force is going to be in this direction. But it's a square building, we're more likely to use SHSs for our uprights here, because we're going to have wind forces coming from this direction as well, equal forces. So we've built that, or we're in the process of building it. The way we would join these two is by welding cleats on here. So we have cleats there, and then we would probably have an end cleat welded on to this member here, like that, so an end cleat on there, and they're bolted together. And once they're all bolted together, so I've got our end cleat on this beam, our cleat welded off there, like that, they overlap, they bolt together. Once that is bolted, and the bolts will have a specified torque as well to ensure that they're providing enough pressure at that joint to stabilise that joint, this will be incredibly rigid. We could put a lot of wind on there, and it's not going to deflect at all in any fashion. It's going to resist that. But we will also be able to achieve large spans between two members. So we can have a massive piece of glass in here, unobstructed, if we wish. So that's one use of the cleats. Another very typical use of cleats, and we can see it on top of these trusses up here. However, they've got equal angles as cleats, which is I guess it's a nice, easy, cheese way of fixing cleats onto the top, because they're always going to be upright if you pull parallel to the top chord of the trusses if you use it equal angle. Can everybody see those equal angle cleats up there? So that is another very typical use of cleats, welded onto the top chord of either a truss or a portal frame to take our purlins, and to fix our purlins too. But in your process of walking around and looking at things, check out the use of cleats. You'll see cleats used everywhere for all sorts of things. Has everybody seen this type of fixing before? So it is becoming incredibly common. And that's where we use a flat piece, or so it's a flat plate of steel used as the base plate to fix our universal beam to the concrete slab. What's going on under here, and what will happen first is we'll pour, well, let's call it a large concrete block. It might only be 300 by 300 or 600 by 600, but we cast a large concrete base plate with threaded rod cast in there. And our threaded rod, preferably, will have a cog on it, so we'll have a bend on our threaded rod, so to resist any uplift and pulling. If we were to just cast threaded rod in there, we'd want to be very sure about our binding with the concrete. We're not going to get, and even if we get fantastic binding with the concrete, apply enough force, take out a chunk of concrete, you're going to take out a chunk of concrete like that. That is essentially your bearing portion of the concrete pad footing, just that small cone. Whereas if you put a cog on there, then that vastly increases our bearing of that member. So have our threaded rod cast in there. Then, and we'll do that to the other side as well. Then we'll spin. So we'll get then the placement of them. These dimensions are incredibly important. So we get those placements exact. But in regards to the height of this concrete, it can do a bit of this if it really wants. Because then what we go ahead and do is we spin some nuts on, and our nuts will sit, well, at anywhere there. So we get the laser level and we get those nuts exactly at the desired height of the bottom of that base plate. Because then when the time comes, our portal frames are lowered in and our base plate sits directly on top of those nuts like that, and then other nuts spun on and torqued up. So that enables us to get that base plate at exactly the right height, exactly the right desired height, and that could be adjusted slightly for if there is something slightly wrong with that portal frame. That gives us some freedom for adjustment. Then, following the installation of our portal frame, so that's in, the nuts tightened up, you put in a non-shrink grout pad under that. So that non-shrink grout pad takes the compressive, or shares the compressive force from the base plate to our concrete pad footing, and shares it with these fixings as well. So we're no longer just relying on the strength of those fixings. We're spreading that load equally through our pad of non-shrink grout, and it's important that, of course, that non-shrink grout is used because we don't want any separation between the grout and our base plate. So that's what's going on underneath. We can have trusses. So in this example, wall trusses constructed from various steel sections, typically RHS and parallel flange columns. We can have roof trusses constructed of the same as well. So in this scenario, we have a wall truss located above a glass fronted shops. Not sure what these X's are, whether they denote any bracing, but this truss can be constructed in a fashion that, if appropriately fixed to these uprights, can also provide bracing suitable for these openings. However, if we were to do such a scenario, we'd want to be using hot rolled sections. This cross section here shows cold rolled sections of steel, so quite thin sections of steel, a millimetre, millimetre and a half thickness. They're not going to provide us, typically they're not going to provide us with the adequate strength for bracing in that scenario. So for this cross section here, that can provide vertical structural support, but not horizontal bracing support. So if we were to use this type of detail, we want to have bracing in there underneath. But here is I'm not going to say it's a typical detail where, because here we've got a universal beam and a gutter, and then a parapet wall and another roof pitched off that parapet wall. I guess you have have a scenario like that, possibly with a sawtooth roof, or with some type of articulation of roof. Not a particularly common detail, but here here's some good terminology to have a look at. It said provide C150.12 girts between truss webs for fixing and cladding. So can anybody tell me what a C150 is? Yeah.
Column 1.
So what is the weight?
Yeah.
With kilograms.
And then in that scenario, the 1.2, that'd be 1.2 millimeter base metal thickness. But because because you're not going to have, I don't think you're going to have a 150 that's 12 kilograms per litre. So, but for that. What have we got? Can anybody decipher this? So provide, with a strange symbol, 20 holes at 2000 CTS in web of gutter support. Anybody tell me what that?
Support? Is more? More?
Molt? Yeah, but So what I said is provide 20 millimeter. This symbol means diameter. So 20 millimeter diameter holes at 2000 centers. So at 2 meter spacings in web of gutter support. And cut portion of CB1 to allow box gutter to pass. So here we see that CB1 has been cut to allow box gutter. Personally, that would be a detail of last resort for me, because essentially what we have look, I don't know what CB1 is supporting, but yes, you've significantly compromised your beam, and you also have to do a fair bit of work to that beam as well. So we'll have to cut through the flange, cut through the web, remove a section of the flange, re-weld the section of the flange on top of that web there. It's a lot of work for a compromised beam.
You could have a beam of half the width.
You could have a beam of half the width. I don't know what,
because that's all you're doing there.
Yeah.
Strength is.
Yeah. Possibly CB1 continues over a column over here, and we've got loads over there that require that to be a continuous beam. Hence, we use that large. But that's why I say that's a detail of last resort. It gets really tricky with box cutters because you've you've got to supply not only a deep enough box gutter, but have enough fall from one point to the other. And there's an Australian standard for determining the size and slope of box gutters, and there's a trade-off. You can go for less slope and have a larger box gutter, or you can go for less depth and a wider box gutter, and choose different size rain heads, etc. So there's all these trade-offs. But essentially what you've got to do is you've got to fit a box gutter in there that is large enough and have enough slope to run from one point to the other point. Now, if you've got buildings which are 40, 45 metres long from one end to the other, you have intermediate downpipes, certainly, but you don't want to go having too many intermediate downpipes in some scenarios, so you're going to have to accommodate really big box gutters. If you don't want to go doing that to your beams, what you'll need to do is have really tall cleats, because we'll need to put our purlins up higher to raise our roof sheets higher to give us space in there for the box gutter. Does that make sense to everyone? However, the issue with having really tall cleats is you end up having not a great deal of strength, because as you increase the height, you increase the moment, and you're going to have thick cleats to resist that. So that may be why they've chosen for that detail. But I would prefer to have beefy cleats and pick my purlins up off my roof and provide adequate space for a box gutter that fits above the universal beam there. Okay, that's something I didn't research. I don't have a lot of knowledge about top hat sections versus furring channels, because I don't typically specify either. Does everybody know what a top hat section is? So a top hat section is called a top hat section because of what it looks like when we cut through it. So, cutting through a typical top hat section, it's like that. So, slice straight through it. Has everybody seen those? They're used a lot for battens on roofs or for fixing plasterboard. So, a very common one is a 35mm top hat section. Typically non-structural, just for fixing. So on top of that, we'll have our plasterboard, then our screw fixing into that top hat section, and then got space in here for fixing into whatever our underlying support. So that's why top hat sections are used, because of their easy fixing. I'm going to have to look at what actually is a furring channel. I think we're talking about C's, but I'll have to check that out. But typically for purlins and wall girts on roofs in cold rolled sections, we use Z sections and C sections. Has everybody seen a Z section before? Is there anybody who has not seen a Z section? No. Yeah? For sure. Right, well, a Z section, it's called a Z because, like the top hat, when we cut through it, we get something looks much like a Z. So, and we'll use those, so up there we've got equal angle purlins, but typically we can use Z sections as purlins. So let's just say it's a really flat roof. I don't want to rotate the board. Having a Z section like that enables us to fix through here into that member, and then have roof sheeting and fix into here, like that. We can use C sections in that application as well, but let's say we supplant our Z section with a C section there. The difficulty can be in construction getting your battery rattle gun or driver or whatever in at the right angle to do that fixing. And so Z sections are far easier to install. Oh, now this is probably a very tricky one. Where is a purlin used and where is a girt used? You could tell me where a purlin is used, couldn't you? Yeah, for roofs. So purlins are used on roofs. Yeah, girts are used for walls. So when we're talking particularly portal steel frame construction, our horizontal members on the walls are our wall girts. People also refer to them as wall purlins as well, but the correct way to refer to them is girts. Also, you'll see if you drive around recent subdivisions around the suburbs, you'll see plenty of cold rolled steel frame buildings going up. Much of the same terminology with the cold rolled steel section frames as with the timber frames. And so in terms of studs, etc., we have cold rolled studs at 70 millimeters, at 90 millimeters, 70 by 35, 90 by 35, etc. However, I think I made mention of this previously in residential, that with your cold rolled steel frame construction in residential, a lot of it is actually based around trusses. So did I make mention of that previously, that if you look at one of these steel framed house frames, you'll see, for example, so this is I'll just quickly do an outline of our house frame. We've got a opening here. We typically have things like a panel there. What are essentially two upright trusses. So we've got two studs, or three studs, there like that. But rather than having noggins, you'll see a lot of these steel frame houses just have webs like that, and then we'll have a section there of horizontal members and then angled members in between. So more and more you see that a lot of the steel frame buildings are made up of what are essentially just a series of trusses. And that does away with the necessity for bracing. Particularly in an area like that, where we've got a very short wall bracing is a difficult thing and has to be engineered. So that's what's...
The furring channel doesn't have the flavors.
What's that?
This furring channel doesn't have the flavors.
Which flanges?
The ones that securing flanges.
Right. Okay, so it's just a C.
Rondo.
Oh, right.
Those little clips secure onto here.
Yes. Yeah. Yeah.
That's maybe what it's talking about.
Yeah. No, that would be what it's talking about. Yeah. So. Yeah. So I'll draw one in cross section.
Maybe furring channels.
Yeah. Yeah. Yeah, great, thank you. Yeah, what Alex pulled up there. So we had our top hat section, which is shaped like that. Our fairing channel is simply shaped like that. Now we may have some profiling through here to give us extra strength, or even some profiling in the side like that to give us extra strength. But because we don't have these flanges on the outside as we do with the top hat section, we have to use cleats in there for fixing, and so they're used as a proprietary system. So you buy these cleats with the fairing channels, and they will fix onto a predetermined member that you want. So yeah, fairing channels are not as versatile in their use as top hat sections. However, because they don't have these flanges, you've got they can be used in areas, in tighter areas. Clip on, clip off.
Because all they all clipped on then afterwards. Fairing channels are clipped onto the clips. They need to get secure.
Yeah.
That would be secure.
Yeah, you do see them tacked in though to the cleats. But I think, in fact, that's a technology, or it's an idea which is not used a whole lot in construction, is the tensile strength in steel, that the ability to clip on. So so much of construction is actually about rigid fixings, where I think there's possibly some room for invention there in quick systems that enable I guess the spring function of steel to clip sections in place, things that are non-structural. So steel sections, can you identify the different steel sections in the image below? No, it's too far away. No, can anybody identify things? So I'll point some things out. Yeah. So what's this fella here?
It's a
That one is
universal.
UV.
Yeah.
Yeah.
Yeah, universal beam.
Yeah.
What is this one up here?
It's a hollow section. Square section.
Yeah, square hollow section. Yeah, this one here, it's a C channel.
Even the one on top of it.
Yeah, I'd say that is a C channel. Yeah, it's a bit hard to. Can anybody see what that one is? On the end there, it's a bit small, isn't it?
It's a Z. It's a Z.
Yeah, it's a Z. Yeah, this is a bit unfair that the students that are sitting in front of the class can.
I'm going to put my glasses on.
Yeah. What's this thing here? Cleat. Yeah, it's a cleat. So so it's a cleat in a purpose I hadn't mentioned before. Here's another cleat over here for fixing to. And then we've got some cold rolled C sections in there. Steel rod. We haven't mentioned steel rod, but yeah. So that's our bracing. And typically, what you'll have in this scenario, off of your cleat, you'll have an angle fixing here with an end plate, and then a bolt behind that. So that bolt can be tightened up, stretch the bracing out. Actually, I took some photos today as well of some other details in portal frames, which I'll bring up a little bit later on. But in regards to that bracing. So we'll see if this thing will work from the slides. So there's the last arc guide. There's no, it's not working. It's just going down. But there are various different guides put out by the steel suppliers and manufacturers, where they contain all the design and engineering information you need, and also online plenty of blocks for CAD as well to grab and to put in. So here, if we look down our menu, we've got so top hat spans, or actually no. It's various different products there for the cold rolled sections. But within these guides, you'll have span tables showing what a member can span, what its where the flange thicknesses are, what its weight is per linear metre, etc. And Rondo. So Rondo typically provide all the systems for internal non-load bearing steel framing. So a lot of ceilings, a lot of the suspended ceilings are done by Rondo. That's where we have furring channels with clips on the end and adjustable hangers to those clips, and they're typically spaced at 600 centres, and you have acoustic tiles which drop straight into them. Otherwise, you can also have various ceiling sheets like plasterboard also fixed to those hangers as well. Reasons we'd have a suspended ceiling are to provide space for air conditioning ducts and services, to hide or basically to hide all this. So all this, we'll put a jump, but all of these, all the services, etc. So in this tape building, they've decided not to have any suspended ceilings, so students can look up and have a look at all the services and look at what goes on.
Also, heating and cooling, reduce your
Yeah, bring the ceiling down lower.
There's always this space up there without heat
Yes, yeah,
or cool.
yeah. So you bring your ceiling down lower to minimise the volume of heating and cooling. Also for sound absorption. So where I guess we're fairly lucky here, we've got a lot of insulation on the underside of that roof. But I don't know if you've noticed that there are plenty of cafes and restaurants where they've decided it's a really cool thing to take out the acoustic tiles and have all this stuff exposed, except they're just really noisy spaces, because you end up having reflective surfaces on floor, walls, and now the roof as well. So those suspended ceilings, particularly with acoustic tiles, make everything much quieter. So for an office environment, etc., that's a desirable thing. And
why
also,
don't they insulate the roof here instead of put the insulating ceiling? It's just to cover all the pipes and stuff, or it's because it's not like it's expensive?
it's because it's
To put insulation on the roof instead of making an insulated ceiling.
yeah.
Why don't they do it very often here? Is it very expensive?
Insulated ceilings.
Insulated
roof.
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 Blankets.
So you can see the
Not
roof,
that.
you can see the structure,
Just
the
like it
beams.
is this one here.
Yeah. The reason we would insulate, well, it's preferable to insulate a ceiling rather than insulate a roof, is because you contain your heat and your coolth more to where you need it. I'll just draw. Let's just talk about typical residential. Typical residential house with pitched roof and a square main portion of the house. This is our ceiling here. Having a large volume up here helps us in regulating the temperature. So it's hot, it's summertime, we've got a lot of heat coming onto this roof. If we were to have a really low pitched roof like that, we get a lot of radiant heat transferred from that sheeting straight through. And so having a space up here really helps with the regulation of temperature. But what we don't want to be doing, so wintertime, for example, we're sitting in here. We don't want all the heat going up into this space. We want to minimise the volume of area that we want to be heating and cooling. So it's best to put our insulation blanket right there. So that contains our insulated area to where we really need it. So in our roof space, we don't really need to insulate that because it doesn't matter to the occupants whether that's getting hot or cold. But what we will also want to do, as well as our ceiling insulation in there, is have reflective foil coming off of our roof purlins as well. And you have to provide space between your roof sheeting and the reflective foil. The reflective foil, that stops that minimises the radiant heat that goes through. It doesn't aid a lot for convection and won't really give you much for an R value, but it will really help with the radiant heat that comes through from the sun. Is that answering your question, or?
Yeah, it's because there's no rain here and there's no snow, so you don't even need a
No.
shape like that. And
Yeah.
from the aesthetic point of view, in my opinion, the suspended ceiling is not must see. It's not nice when you can see your beams if they are in timber beams or something like that.
All right.
But you need to have a packet of insulation between
Yes.
the beams and the actual roof.
Yes.
So I was wondering, is it because that stuff is expensive? You don't find
Right.
it here, or
Gotcha. Yeah. Yes, it is expensive.
Blankets.
So yeah. So if we're doing, let's do our raked ceiling in here like this. So we want our exposed beam to our cathedral ceiling. Well, no, we can tie it together. It's whatever. We've got our exposed beams happening up in there. Let's say they're like 200 depth or so. We're going to have at least 35 millimeters for our plasterboard supports in there, plus 10 millimeters. So we're down to 45 millimeters already into our 200. So we're going to have to fit some insulation in there, but we've only got 155 millimeters left in there. And so if we were to fit insulation behind there, we're not going to fit a standard insulation blanket behind there, because we're going to need about 250 millimeters at least for that insulation blanket to go out. So we're going to have to use things like polyisocyanurate panels, or something that has what's called a high K value, which is a high insulative value for its thickness, for its depth. Those things are expensive. So we can get a 50 millimeter PIC board and fit it in there, and then our 35 millimeters, etc., and we see a little bit of timber left at the end of that, so we can still have some exposed timber beams. Or we can go the even more expensive option, which is, I think it's called aerogel, which is it's a thinner gel type blanket. I've never actually seen it. I've specified it because it's the only way you can get decent R value in a very compacted space. But beyond those two options, which are quite expensive, we would have to have very deep beams in here to have our 250 millimeters of insulation, then ceiling, etc.
Couldn't you go cladded, insulated cladding?
You could,
Like a foam or a something else.
certainly you could. So
Instead of a iron sheeting plain,
yeah,
go above rather than below.
yeah, definitely, and that is a good approach. And that those insulated sandwich panel products, they haven't been around for too long. They've been around for sort of 4 or 5 years. Yeah.
In Europe,
So,
they've been a long time.
yeah. Australia does lag behind the rest of the world in some aspects. So that's sort of one of them. So yes, we could have our panels on the outside, which are which we've got to either have that PIR foam in there or expanded polystyrene foam. Expanded polystyrene has issues with fire and things like that. If you were to have a fire, it spreads very rapidly. But you can have that, and then you might get enough of an R value out of that for our climate zone 5. Not sure. You have to look at your products.
You have to see each product, what's the characteristic.
Yes, you will. But that's one good option of being able to have exposed rafters and
when
so
they
you put
do
insulation on the outside.
plan roof, they put a double ceiling. I mean, they put the roof and then implants and then ceiling. When it's a flat roof.
Yes.
They do like, I mean, when you build a house that has a flat roof.
Yeah.
They do the same process. So they put all the air conditioning and stuff, and then a suspended ceiling.
Mm-hmm.
Or do they put all the stuff on the top of the roof?
Putting all the stuff on the top of the roof is it's an older way of doing it. If we wanted to have, well, let's talk about air conditioning. If we wanted to have an evaporative unit, which is very energy efficient and works well in a dry climate like we have in South Australia, then we would have to have that unit sitting on top of the roof, and then we'd have to find space for running that ductwork in the roof on top. But what is also used a lot, and what's probably a good option for that scenario, is a split system, where you have a compressor unit on the outside, and then pipes running to your condenser unit, which sits inside. That way, you're not going to have any space for running services. You 25 millimeters.
You know ducting.
Yeah.
No ducting.
No.
Bring that up like that. Bring it.
Yeah. But with our flat roof, we do a cross section through that. One way of doing a flat roof is with webbed trusses, because we want to span a long distance. So let's say we've got 300 deep webbed trusses. So we have steel webs running between those. Typically there's space to run air conditioning ducts, certainly that way, and then if we do a cross section through the other way, plenty of room for running air conditioning ducts through there, and then having our ceiling gear or ceiling running there, air conditioning duct a bit up, and our insulation there. So that's also a possibility for flat roofs, for running all your air conditioning ducts inside the roof space. But when you talk about what do we typically do in Australia? Well, typically we just build houses like you see in the suburbs. That's 95% of it. Then there's your more interesting sort of bespoke approaches to building, and in that scenario, you've got all sorts of different approaches that people choose, and lots of different ways of getting around issues like that. So, case specific, yeah.
Thanks.
That's all right. So portal frames, yeah, I like portal frames. I reckon they're a great way of building. They, and we'll see a bit more, but they enable so much. So portal frames are a bulk active structure, i.e. all load transferred through the bulk of the structural form. So rather than have independent structural elements like a wall frame, a roof frame, a floor frame, etc., it's a structure in and of itself, and it's all tied together. So portal frames are made in a variety of shapes and sizes. They are usually made from steel, but can also be made from concrete or timber. I saw a large warehouse down, I can't remember the name of the area. There was back when there was a really large oil recycling plant fire, Wingfield. There's in Wingfield. Right next to that was a factory that we went in that had massive timber portal frames, like big plywood gusseted joints. It was actually really interesting to see. Beautiful looking structure, but definitely not at all common, but they do exist. I guess because it's much quicker and easier to use steel. So steel can be welded, have end plates on there, bolted together, put together incredibly quickly. A timber portal frame, has to be, it's probably a little bit more involved in the design process and more involved in the construction process. The portal structure is designed in such a way that it has no intermediate columns. As a result, large open areas can easily be created within the structure. I'll just quickly go. So there's a couple more photos from today. Photo 3. Yeah. So that's a machinery shed. Also hay sheds. So I don't know if anybody knows these tractors, but if I was standing next to that wheel, I probably wouldn't be as tall as that wheel. So we're talking about very large structures, very large spans available, or very large unsupported spans available from these portal structures. Essentially what we have happening here are several different portal frames. So portal frames happening in this section and a large portal frame happening to create the opening there for driving machinery in and out. And just quickly show some other photos I took that. So an apex joint. So we've got plates welded onto the end of universal beams and bolted together. That's a very simple apex joint. And Z sections for furlets. And an eaves joint or knee joint in the portal frame. This one has flange stiffeners in here and flange bracing. That's a very typical detail. Also, what is also very, very typical detail. So in this, we've got our flange stiffeners running perpendicular to our flanges, but also what's a common detail is so our universal beam and our eaves joint there like that. Our flange stiffeners running directly in the same pitch as our rafter pitch. That. But that, yeah, and these ones have got this bracing unit in there as well to provide strength there. So that sort of construction gives you a lot of freedom. Gives you a lot of freedom for the internal floor plan because you've got no columns there, and it gives you a lot of freedom in regards to openings because you don't need any bracing. So if we have a look at our openings here, massive openings, open all to one side, no bracing whatsoever. We have bracing in other sections where it can be, because where our shed is longer this way than it is in this direction, the majority of wind force is going to be coming from that enclosed backside there, and so we're going to have to include bracing in this wall to resist that. Well, it's going to be cheaper to provide bracing in here than have a really sturdy portal frame provide that bracing. But if we wanted to have this end open as well, we can use larger members to create a portal frame to provide enough bracing as well. So portal frames are generally used for single-story construction, which require a large unobstructed floor space, such as factories, shopping centres, and warehouses. Has anybody seen people using shed frames for houses about the place? I've seen it. I've seen it around a bit.
What about the shed houses?
Well, yeah, that's That's So people refer to them as shed houses. Neighbours of ours did a very attractive looking one. Just quickly bring on the internet. No. Yes, exactly. No escape. There we go. It's happening eventually. So a good option in here. This style of building, in fact, can anybody offer me what a name for this architectural movement? Something else. So in architecture you have various different movements, modernism, deconstructivism, all these isms. I don't know what this ism is, but it's like how do we say it? Minimalism. Essentially, but there's actually a fair bit of this going on at the moment of people building very modern style housing that references the traditional sort of steep pitched roof and very simplistic square or rectangular floor plan. Here's another example of that. For creating this type of look, yes, obviously it's a lot about hiding gutters and keeping lines simple and being, toy town look to it. But to create such a structure, it's incredibly simple to do that with portal frames, and to do that with going to a shed manufacturer and saying, look, I want a house to be in this very simple rectilinear fashion with a steep pitched roof, and shed frame manufacturer will go, cool, that's really easy. That's what we do all the time with our steel portal frames. So you can do stuff which is cutting edge, but it's also very cheap to build because it's very easy to fabricate the portal frames for doing that. And then your openings are only dictated by where you're going to be running wall girds and things like that. Obviously, if you want to have gutters, you've got issues there with your details around gutters. Various different ways of skin a cat. There you have larger standoff cleats for your wall girts, bring your walls out slightly, and then have a profiled gutter to fit within the roof also. But I just thought I'd show that. That's a very contemporary, very current architectural movement, which can be done very easily with shed frames. So advantages: speed and ease of erection, incredibly quick to put up. These steel portal frames can be quickly closed in and made watertight. So if it all goes to plan, these frames go up incredibly quickly. Obviously, with the larger ones, you need scissor lifts and cherry pickers and whatever to get up to those sort of heights, because you've just got very tall walls, very large open spans. But yeah, it's very quick to put up. Framework prefabricated in a workshop and not affected by weather. So when you're building your timber frame on site, it does take time, and you may have rain, etc. Site work such as drainage roads, etc., can be carried out until the framework is ready. Carried out until framework is ready for erection. Don't know exactly what they mean by that. Because that's really the same as any construction process. Know where the hold up during erecting the framework, particularly if you're using steel. If you've got a hard compacted rubble base to work off, then working in all weather is typically fine. Connected together in factories by welding and site connections should be bolted. Disadvantages: although steel is incombustible and has poor resistance to fire, as it bends easily when hot. Has anybody seen
Creep.
Yeah, creep. Yeah. Has anybody seen a steel portal frame after a fire? Yeah, that's a good example. But yeah, you don't have to go very far from Adelaide. So the pinery fires, which happened about, it's probably getting on 2 years ago, a lot of hay sheds went up. There was, from up in the hills, you could just see hay sheds burning, like lots of them burning. To drive past those soon after the fire, before they were demolished, yeah, you just had all sorts of shapes and so on from the steel just melting with that heat. So steel behaves differently than timber does in a fire. Timber will maintain its structural integrity for a long time. You provide heat, but it's always as strong as the uncharred section of the timber. So you've got charring happening on the outside, but that centre core, which is not charred, maintains its strength as it would as a natural piece of timber. But steel doesn't. So steel will stay strong and then get to a certain point of where it's hot enough, and it will start bend and creep and flex. And so it can be, I'll say it, unpredictable in how it's going to move, when it's going to collapse, and how it's going to collapse. Also subject to corrosion, particularly with your smaller cold rolled sections. A lot of your hot rolled sections have sufficient mass to inhibit corrosion. But yeah, I was just talking to somebody today about design of piggeries. So there's a thing called eco shelters where you've got large concrete bollards and then curved roofs over those. And the old eco shelters were built with steel columns on the inside, well, flush with the concrete blocks and bollards. And those sections rust out really quickly because they're in contact with glue and things all the time. So they're built with concrete panels on the inside, and those steel columns located on the outside where they're away. So from things like that. So it's something to think about. What they're going to be in contact with. So that's even large steel sections rusting out significantly because of that. There was something else. Yes. An important thing to think about with steel portal frame design is transport. How you're going to get those pieces to site. So you're limited by width. So approximately 3 meters wide is your maximum for your semi-trailers without wide load and escorts, or 15 meters is about your maximum length. So that's why you have all these bolted connections. So everything can be fabricated in the factory, ready to bolt together, but then come onto site in small sections, be delivered, and then framed up and bolted together on site. And that brings me to another issue as well with portal frames is weight. And if you have portal frames which are already bolted together and brought to site, or already bolted together and then lifted up on site, you need adequate cranes, or an adequate crane for lifting that sort of weight as well at whatever boom length or boom extension it has. So that's some details in regards to portal frames and some terminology. So portal width, height, rafter, roof bracing, purlins for roof support, girts for side sheeting, our pad footing, our eaves junction, our apex junction, those terminologies on the site. Not all portal frames have bolted connections. Some of them have bracketed connections. So with that timber portal frame I saw, that had large plywood brackets, but you also have steel brackets as well for your connections. This is more the scenario with your smaller residential sheds. I guess probably a lot of people would have seen that with your Stratco sheds that are 6x9 or so, these type of details and junctions. Yeah, it says here knee bracket or haunch. That's not to be confused with also in portal frames, there's also another thing called a haunch. So here's our eave junction there. They can also be braced with, so this is a hot roll, so this is a couple of universal beams, and then with another universal beam, we chop out a triangular section, keeping the web intact, and then that is typically welded to this flange here, end plate and bolted on there. That's also called a haunch. That provides additional strength to that knee junction or eaves junction. Under load, with our apex, you have what's called a sagging moment, which is going like this. So you have the tendency to sag like that under load. But with your eaves junction, you have what's called a hogging moment, which is where, which is the opposite to sagging, which is bowing like this. So that's your results of your sagging moment. That's the result of your hogging moment, and the haunch here is to restrict that, so to stop that from happening. So we're bracing in this fashion in there like that. Some more that's typical machinery shed, large factory type construction. Have a header beam in here to help take weight over an opening and provide stiffness over that opening. Got mullions for fixing the roller door too. So portal framed intermediately, so that's our mid portals and our end portals or end frame. Also typical mullions in your end frame like that, because we can't have our Z sections spanning from one side of the portal frame all to the other. So our wall girts there, they're not going to span from one edge to the other, so we need mullions to support them mid-span. Also a fascia purlin in there, so a purlin right at the edge here for mounting your gutter and for taking your roof. So that detail doesn't have a fascia purlin. It's actually got cleats and the cleats to support the fascia on this one, which is actually probably the more typical detail. So we have our purlin further back here. We have a large saddle cleat. Now that may be a flat plate cleat, or it may be an SHS cleat. So a piece of steel hollow section or square hollow section, welded to our beam with a plate welded on the end that we bolt our fascia to that supports our gutter. Is that fairly clear from where you guys sit? That detail? And there we've got our haunch in there at our eaves junction. The legs or stanchions of the portal frame being connecting at the bottom to a foundation. Here you can see the base joint connection in place. Been through all of that. Here is I don't think it's called a haunch of the apex joint. Not sure the exact terminology for when we brace the apex joint like that. But once again, those braces to the apex joint are made with a piece of I-beam as well. So it's a piece cut out of an I-beam, and then that is welded on to our plate. So our rafter there, that, and then let's call that our apex joint stiffener. It's going in under there.
They call them gusset pieces in the snow.
Gusset pieces. Oh yes. So let's put, yeah. All right. Well, let's call them gusset pieces. Yeah. So yeah, a gusset is anything that braces in a triangular fashion. Gusset pieces to the apex joint. That will be welded to our plate like that, and then welded along there as well. And then we may have bolted fixings through here like that, or likely to have bolted fixings through there in that fashion. Yeah, gusset pieces again used to increase strength. Covered that. So, as with any type of framework, stability is important, i.e. movement to help strengthen the framework and prevent movement. Diagonal bracing can be used. So, same as bracing in a house, except we use much larger pieces of steel. So we use things like equal angles, or sometimes even SHSs for bracing. So our portal frame girts, either C sections or Zs, but Zs are used a lot because they make fixing easy. Important thing for designers are thinking about your details. So it's not just about thinking, all right, this is what we want. We want bricks at the base. We want a little bit of flashing coming under our sandwich panel cladding, etc. How you got to think about how all that's going to butt in at the end. And so this is provided as an example of a horrible, poorly thought out detail. You know, the way I would do that is I would have specified that the block work come out to this point, and all your open sections can butt up against that block work. Do the simplest. And that's it for portal frames. However, well, that's it for the slides. However, I'll just quickly show you a few other things if you don't mind. In regards to I'll show you one other thing. So it's this, and this is actually about geodesic domes. So when we think about portal frames, it's not just about universal beams bolted together, etc. You can create portal frames with trusses. You can create portal frames with triangular trusses. Has anybody seen that scenario of a portal frame? Could be. But was anybody ever seen a triangular, like a truss which is triangular in cross section? I'm sure you would. You would have. Used in sports stadiums and things like that. So we've got, let's say it's a curved one. We've got our curved truss going like this, and then we've got webs doing all this sort of stuff. But if we were to cut through here, the section through there, and look at that, we've got this scenario going on. Yeah, people seen those? And then we might have some at, at vertical, further back, etc. So
those beams where they have like with sound gigs, they hang up the light.
Yes.
And,
Yeah, exactly. Yes. So on the front of stages, so for when you get really big stage setups like at One Adelaide or whatever, you've got these big aluminium triangular section trusses, big curved ones that go over. Yeah, exactly. But yeah, they're also used in permanent structures as well. But actually, I think that is a really good space to look for innovative approaches as well. Is in non-permanent structural design, like in stages and things like that. It's fantastic thing to use there. But so portal frames don't just have to be universal beams. You can make them out of triangular section trusses as well. But has anybody ever heard of a geodesic dome before? Yeah, not surprised somehow. But yes, a geodesic dome it's a dome that's made up of triangles, and essentially it's like it is a truss that is curved and is supported from all sides in a circular fashion. Has anybody been to the rectangular stadium over in Melbourne? Soccer stadium in Melbourne. Yeah. So that's what this video is on. It is a spectacular structure. Essentially, this is the concept of portal frame on steroids. So it's portal frame taken to the extent of a geodesic dome, then chop some sections away, join geodesic parts of geodesic domes together. Certainly, I have seen geodesic domes used in residential architecture. Certainly not very common, but where we have multiple geodesic domes joined together with sections cut away, I haven't seen. But this is where we've got
new rectangular stadium in Melbourne.
public architecture driving new innovations.
Place from here, but I'm told the best spot to view it is from up there. The view from here is spectacular. Melbourne never looks so good. But of course, we're here to see the roof of the stadium. There are more than 2,000 individual tiles in that roof. You can imagine how difficult it must have been to get them all together in the right order.
The shapes come about by a number of parameters. One, of course, is that we wanted to put the spectators in the best positions.
But another design priority is what sets this building apart. To make the structure as lightweight as possible. This stadium is taking the science of structural engineering into new territory.
The idea of doing more with less is critical to how we go about doing design work. So it turned out with the technologies we want available to us today that this structure is a very, very efficient and light way to do it.
They've designed the roof of the stadium using a series of geodesic sections. The geodesic dome was first popularised by the American architect and futurist Buckminster Fuller. Put simply, it's just part of a sphere made up of triangular panels. The beauty of this geometry is that the forces are distributed so effectively, the structure can be both lightweight and self-supporting.
We took those ideas of shell action from the likes of Buckminster Fuller But of course, with the stadium, we have a big hole in the middle that we've got to deal with. So we came up with the idea of actually putting a series of shells together.
Each individual shell has all the benefits of being a geodesic section. But the shells also support each other. And it's that unique combination working together that allows the creation of this very light structure. So you've got some physical models for the roof here.
Yeah, it's the best way for us to actually understand what's going on. There's nothing like having something you can actually pick up and understand. So each of the shells are different, but at the same time we had to get structural efficiency into it. So the shells themselves actually span between the groins, or what we call the cantilevers, that run between each of those. But they actually sweep up and down across the stadium. So at the front there's sort of an arch action on the east and west sides. And it's those forms that actually give the roof the ability to carry load.
When you look at this roof, you're struck by how complex it seems. Calculating the forces in a structure like this can't be easy.
Really, it's the technologies that we've got today that have actually taken it forward. This one has actually used a lot more advanced analysis work.
In previous years, figuring out the size of each piece of steel in the structure was a long and tedious process. Now, they've automated the task, so they can run through hundreds of different options to come up with the lightest design.
And what that means is we end up each time taking a little bit more steel out of the roof. What we regard as one of the key parameters when you think about the kilograms of steel used in this building per seat. This building's probably 10 times less than what was used in Beijing per seat. We feel there's a great beauty in that, where the structure needs no more than it has to actually keep it up. Every piece is in its place.
Because the shells all rely on each other for support, until every piece was in its place, the roof wasn't self-supporting. So when the last section was bolted in and the props were removed, the structure was really put to the test for the first time.
I think the thing that was really great for us was when we pushed the roof up, pulled the props out and let it come down in its own right. It moved exactly the way we thought it would do. So, yeah, there's a sense of great relief. It's always great relief, but it's also a milestone in knowing that all that hard work over years has sort of paid off. When you do something as adventurous as this, it's not like buying it off the shelf. But its complexity has been borne out in the building process where, as you can see, we've got it up, and it's been a long and wonderful process to get there.
Well, now it's the moment of truth for this stadium. The very first game ever is about to be played here. It's between the contractors for the project. So we've got the architects versus the engineers versus the builders. Even the lawyers have got a team in. Okay, amateur touch footy probably won't draw the crowds this place was built for. But when professionals take to the field, the stadium and its extraordinary roof will really shine.
So that's basically tonight's concepts. Taken a bunch of steps further. Yeah. But certainly, as you know, as I was saying here, is that technological development in the interface between engineering and computer-aided drawing that has enabled this sort of the engineering of this to happen. In a residential sense, it's not that far in the future either. So yeah, clients might take a lot longer to come along, or councils, authorities might take a lot longer to come along. But the engineering possibilities, the access to the engineering possibilities, possibly not that far in the future.
I think there's a geodesic home somewhere in the Mitcham area. I just saw it driving around, sort of where Bel Air Road is.
Right.
There is, it's around Goa, but there is another one. There's a couple of restaurants.
It would surprise me if the residents left, because how are you going to fill the space inside? It's real tricky.
Yeah, and you're gonna have issues meeting National Construction Code in terms of insulation and so on as well. But you know, you can use standard panels to regular infill sections, whatever. But the possibilities are there. I just thought I'd show you that, because I think that's a fantastic build.
In Norway, they built, I think there's like snow for about 6 months a year or something. They built the glass geodesic dome,
Yeah.
and in there they built their house, probably a cold house or something. But they could grow vegetables and stuff the whole year through, because it was always warm and they had to dress up like for in the snow.
Yeah, it's like living on the moon.
Like
in
a
Norway.
paradise in snow.
Yeah. Well, it's a giant glass house.
Yeah. Well, the house was inside.
Yeah, it's like it's like the arboretum at the Botanic Gardens.
Yeah.
So, yeah. All right, so have a fantastic fortnight. So once again, won't see you next week, but I'll see you the following week. That's great with your assignments. Certainly, if you've got any issues. Oh, look, also that's another thing. I haven't been able to access my email from a phone at all for the last week.
It's the same. For me,
Same for you guys.
Yeah,
Yeah.
fixing it.
Yeah, awesome. Well, actually, I better stop recording.
But if you just go to Outlook, if you've got it installed on your computer,
Yeah.
and just use the other login, like